Hi everyone, this is the next section in Notes 2.7, and this time we are going to be proving segment relationships using the two-column proof. I'm actually doing this video in my classroom, so it's definitely echoey in here, and you're going to hear the bells. Hopefully nobody comes in and starts distracting me. Okay, so in the last section we were working on getting used to the two-column proof method, using things that we know, solving algebraic equations. Now we're going to add in the geometry, and we're going to be starting to look at the segment addition postulate, which we're pretty familiar with, but we're going to be doing things inside of the two-column proof structure. Okay, so postulates that we already talked about actually in Chapter 1, the Ruler Postulate. The Ruler Postulate says that points on any line or segment can be lined up in a one-to-one fashion using a ruler, and you can use those numbers to find the length of a particular segment. So in this case we lined up our ruler, and it looks like our scale is in inches, and this particular segment AB would be 3 minus 0, or 3 inches. We've used quite a bit the segment addition postulate. Remember, postulates here, postulates are left accepted, unproven. You know, we don't have to prove them, we just accept them at face value, accept them as fact. And you hear me say the words over and over, the whole segment equals the sum of its parts. So here, the entire segment length AC is equal to the non-overlapping parts, segment AB plus BC. So that's all the segment addition postulate is. Now, if we had a longer segment broke up into, more than 2 segments, well, that's going to equal each of these segments sum. Okay, so we can keep going on and on. It doesn't necessarily mean that there's 2 parts. It just means that the whole length of the string, if you will, is equal to those pieces that you cut it up into. Okay, we talked about properties of equality in the last section. Well, those same properties of equality apply to geometric shapes, and in geometry we talk about equality as congruent. Remember that the word congruent here, congruence, stands for equal measure. Equal measure, that's the direct translation. We can apply those same properties to segments. So reflexive property of congruence, an example would be that the segment AB is congruent to itself. That's a good example, okay? And if we drew that, we had AB here, we could say that it's congruent to itself. Symmetric property of congruence. Well, if we had segment AB congruent to, let's say, segment CD, well, then, and I'm going to put the then in, CD is congruent to AB. We're just flipping that around in a symmetric way. And then the transitive property of congruence, if AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF. So if, again, I got to write my if AB is congruent to CD and that CD is congruent to something else, in this case EF, then the original AB is congruent to EF. So we're kind of transferring that congruence property or equality, equal length, equal measure, across another entity. Okay. This first example of a proof is important. That's why I have it starred here, so please pay attention to that. All right, we are saying, or we're being told here, that if AB is congruent to CD, then AC is congruent to BE. Remember that the if part is the hypothesis. Okay, that goes up here in the top, that's the given, and the then part is what we are trying to prove. So please remember that. I see a lot of people putting that them or taking the then part and thinking that's part of the given. That's not correct. That's going to be all the way down here at the bottom. That's what you're trying to get to. All right, AB, segment AB is congruent to CD. Before we do anything, we mark the diagram. AB is congruent to CD. It's marked. That's been given to us. Now, if they are congruent, then their lengths are equal. That's what this next statement is. And this is the little nitpicky thing. That's the definition of congruency. If two segments are congruent, then their lengths are equal. That's the definition, equal measure. That's what congruency means. Now, BC equals BC. BC equals BC. Guys, notice what I just did. I marked BC as itself. It's equal to itself. Something equal to itself, we look at ourselves in the mirror. That is the reflexive property. Reflection, think of reflection. AB plus BC equals AC. So we're saying this segment here plus this segment here equals the whole segment. Hopefully you see that that's the segment addition postulate. Now, please don't put addition. If you write addition here for this line, I'm going to assume you mean the addition property of equality. That means we're adding the same quantity to both sides of the equal sign. So make sure you're writing this out, segment addition postulate. Okay, the next thing here, CD, right here, plus BC, let me write this out, CD plus BC, it's starting to look like the segment addition postulate, equals AC, that's this segment here. What? That is not segment addition postulate. The segment addition postulate would say that this piece plus this piece equals BD. So what's going on here? We have to decode that and figure out what's happening. My advice is to look at the row above it. Now, AC is identical here, BC is identical here, but AB has been replaced with CD. What's going on? Why is that the case here? Well, that's the case because they are equal. So we are replacing AB with CD. That's all we're doing here. We're replacing it. What does replace mean? Replace means substitution. So be very careful. Even though something looked initially like its segment addition postulate, when you really look under the hood at the details, it was not. It was just substitution. All right, next line. CD plus BC equals BD, this whole length here. Well, that does look like the segment addition postulate. So the whole segment there, BD, does equal the sum of its parts. So that is the segment addition postulate. And now AC equals BD. How did we get there? Well, if it looks like it's coming out of the blue, you really need to look closely at the two rows above it. So if we look here, we've got CD plus BC. Right below it, we have CD plus BC. Those are identical. So this is quantity number one. I can almost even black it out. These guys are identical. If this box, this red box equals AC, and the same red box equals BD, well, this is pure transitive property of equality. We're transferring our equality across three different entities. One entity is the red boxes. Okay, that's one. They're identical. And then we have two with AC and three with BD. So this is transitive property of equality. And finally, if their lengths are equal, then they are congruent. That is the definition of congruency. So I really think that this problem here can look a little bit complicated, and I strongly, strongly encourage you to reread and go over this one problem several times in order to fully understand it. You will definitely see this type of problem on an upcoming exam. Example number 2. Prove that if AC equals AB and AB equals BX and CY equals XD, then AY equals BD. There's a lot of information there. Remember, the whole if part of this is the hypothesis, which is the given. And the piece after the then statement is the conclusion, which is what you're trying to prove. All right, before we do anything, we mark the diagram. AC equals AB. AC equals AB. AB equals BX. Well, if they're equal, that's also going to be a single slash. And CY equals XD. They're clearly shorter, so I have to use 2 slashes to mark them. We need to prove that AY is equal to BD. First things first, we state the given. We've got AC equals AB, AB equals BX. That was the given. That was given to us. Notice they didn't mention this part of the given, and that is part of the given as well. So look for that. That's right down here on row 3. So don't be fooled. That's part of the given there as well. All right, AC equals AB and AB equals BX. We're looking at the transitive property. We're transferring across 3 entities. If AC equals AB and that AB equals something else, then AC equals that something else. Transitive property of equality. Now, AC plus CY equals BX plus XD. What is happening here? Let's take a pause. Personally, I think we need a medium step in here between the 3 and the 4. I'm going to call it 3A in order to highlight what's happening. We have an equality statement here, CY equals XD. And see how you've got the CY here and the CY here and the XD here and the XD here. Clearly, we're not adding the same value here, addition property of equality, because they're different. So I feel we need a little bridge here. Let's say CY plus AC equals XD plus AC. There we have here the addition property of equality. We added the same thing to both sides. The thing that we added was AC. Now, what's bridging between that row and here? We've got the AC, and we've got the CY. Nothing's changed here on the left. But in this case, we have XD here, and the BX has been replaced with AC. You see that? And we're replacing it because they are equal. So in this case, that's pure substitution. Now, let's look at number 5. AC plus CY equals AY. Let's go over to our diagram. AC plus CY equals the length of the whole. What do we call that? Segment addition postulate. And look at the next row. BX plus XD equals BD, the length of the whole. Again, segment addition postulate. So that's why those two are together in number 5. Now, how do we make the conclusion that AY equals BD? If you look at this above here, we've got 2 quantities here that are equal to each other. Okay, 2 expressions, if you will. And here are those 2 expressions below. So I can simply replace or transfer their equality across these entities. So we could either say that this is transitive property, or you could say substitution, because I think really that's rooted in substitution. Okay, moving on. Example number 3. Given GD is congruent to BC, and BC is congruent to FH, and FH is congruent to AE, prove that AE is congruent to GD. First things first, we mark the diagram. GD is congruent to BC. BC is congruent to FH. FH is congruent to AE, so all of those are single slash marks. Prove that AE is congruent to GD. Okay, so we've marked GD here equals BC. BC is congruent to FH. We're missing part of our given here. FH is congruent to AE. Same thing, given. Well, we've got all these little nitpick things here. By the way, that just doesn't look like an E. Okay, so the nitpicky things are that if two segments are congruent, their segments are equal. So let's just write all that down. GD equals BC. BC equals FH. FH equals AE. This is the definition of congruency. And I'm using a stylus that is not that good. So that's why everything looks messy. I'm going to abbreviate here with the congruency symbol. All right, number 3. Hopefully you can see that we've got some transitive property coming up. So we've got these here. GD is equal to BC. BC equals something else. Therefore, GD is equal to that something else. That is transitive. And, okay, so we've got FH equals AE. So I think I'm just going to go ahead and replace that FH with AE. So I've got GD equals AE. And that was really just substitution. I replaced that because they are equal. And finally, number 5, we wanted AE congruent to GD. So I'm going to flip this around here. AE is equal to GD. What did I do? I kind of swapped that around. That's the symmetric property. And this is just the final nitpicking step. If they are equal, then their segments are congruent. And that was really the small little extra step we were asked to prove. So that is the definition of congruency. And I think that's the end of the notes, so hopefully this helps. These are very tricky, and it takes a lot of practice to get used to seeing, this alphabet soup with all these letters on the page, and it's very easy to get lost in these proofs. So just take it one step at a time, but definitely requires practice. Thanks for listening.